Good morning, good afternoon, good evening, wherever you are on this planet, and welcome to our Citizen Science Q&A. Today, we are going to talk about citizen science, and my name is Franck Marchis. I'm the Director of Citizen Science at SETI Institute for Unistellar, and with me, I have Sgro.
Hi, I'm Sgro. I am the Exoplanet lead scientist for the Unistellar and SETI Institute Citizen Science Network, and also do a lot of outreach.
There was a lot of citizen science said in this introduction.
Yes, can you tell that that's the theme of what we'll be talking about today?
We're going to be talking about citizen science. All right, so we are going to talk about a very specific citizen science program. For those who are not aware, we are talking about specifically the citizen science program of Unistellar, the digital telescope that you have one here. This is the Odyssey. And further away, you have the Eviscope 1. That was one of the first ones. So we are going to talk about some results and take some questions from you about our programs and give you some updates as well. All right, let's talk about something super fascinating. I'm sure people will love it. TXDL.
Yes.
So what is that?
So this is one of our results from the Citizen Science Network. This is a variable star that's a Cepheid variable, which are used as standard candles to estimate distances to those stars. Now, the American Association of Variable Star Observers, or AVSO, we work with, and they give us interesting targets to observe with the network. This particular star is a little bit weird. It has a period of 6 days, and that's kind of strange for its particular type. And its period seems to be changing over time. It could be decreasing, especially over the last 20 years. So we've set the network on it to get observations and measure its period ourselves. So let me show you really quickly this awesome.
So why are you doing this? So our users, basically what they do, they use the Cosmic Cataclysm program. There is a TXDL alert specifically. They click on the icon and the telescope will move to the right location. They take an observation that's, for this one, I think it's 20 minutes or 15 minutes roughly.
Yeah.
And what you have here is a report that we send to the observer. So what do we see here?
So here you can see the observer, thank you, Michael Prim, for this observation and what it looks like through their telescope. But on the lower part of the report, you can actually see the light curve from all unistellar observers that we've been gathering. So we've been observing this target since August, and you can see the change in brightness that happens very consistently over this period of 6 days. So you can see the star brightening and then dimming and then brightening and then dimming and brightening and dimming. So this is a really fascinating result because we can get the full light curve, then measure the period ourselves and continue to monitor it, especially in case that period changes.
Okay, so the yellow dot here is the observation of Michael.
Yes, correct.
He took it when the star was faint, in fact, interestingly, and the dimmest. And the blue dots here
are all previous observations made with the Unistellar network by various observers.
So we have a lot of observations here. We're talking about what?
We have a lot of observations.
That's something like 40, 50?
Probably closer to 100, especially now, if not more.
All right. And this is a target that is observable at the beginning of the night, I'm assuming. That's probably the reason a lot of people observe it.
Yeah, those are the best ones.
The best one, right? All right. So that's a 6-day period variable star. But the period may be changing. So we need to continue to observe it to see maybe some changes. And we're going to combine that with other data taken by other telescopes. We're not working in a vacuum. We're working with other astronomers, of course. So this is a collaborative efforts with the AVSO. What is AVSO?
American Association of Variable Star Observers.
Good. Now we know. All right, great. That's a very cool result. I love this light curve. Okay, I want to talk about ACS3. ACS3, you probably know it's the NASA prototype. It's a solar cell that was launched, I think, a month and a half ago, 2 months ago. And they started deploying the solar cells. So we have collected observations from 40 observations since the launch of the solar cell. And we have seen basically the brightening of the satellite due to the deployment of the solar cell. Something surprising to us is that there is a huge variation in magnitude, so in brightness of this object. It goes from 2 magnitude to all the way to 10. 10 is faint. 10 is you cannot see it with naked eyes. 2 is as bright as what's magnitude 2? Sirius, maybe? Something like that. It was very bright in the sky. You will see it. So I observed it myself, for instance, from Boise, Idaho, when I was there, using our Odyssey telescope. And the cool thing is that when you go on our satellite page, you find whether or not it's passing above your head using our prediction. You click once again on the icon, the telescope will move to the right location, and you can start recording just at the right time. And what you will see is this.
Let me show you.
She was not ready.
I was so involved with what he was sharing.
We missed this part. We practiced this one.
We're getting better. We're getting better.
So you're going to see this in your telescope. So you see stars, of course, and then
you will see. There it goes.
There we go. That's ACS3 passing in the field of view. It's moving with respect to the stars because it's a satellite which is orbiting Earth. The cool part is that when you point the telescope in the right location, if you look the location of the telescope, where the telescope is looking, you will see ACS most of the time. You will miss it if you look at the sky like that randomly, but if you look at the direction, you see ACS passing by. It's a beautiful object. Why we care about observing it? Well, first of all, we want to understand the brightness of this object, kind of refining the way solar cell brighten. We know it depends on the orientation of the solar cell with respect to us. So it's like, imagine like I'm floating in space and I'm carrying a gigantic mirror the size of a tennis court, to give you an idea. And I can move this cell. So if I point this mirror toward you, it will be extremely bright if I can reflect the light of the sun, right? So, and if I'm slightly tilted, you will barely see this mirror, but the reflection of the light from this mirror, because the surface, basically reflected surface, is small. So that's something like this we're trying to understand. Additionally, we know that NASA is testing now the motion of the satellite using this solar cell. So it's like sailing on water, basically. But in this case, we use the photons coming from the sun to steer the satellite and moving it up and down. So they're working on that. And we use updated TLEs, which are basically the parameters of the orbit, to be able to see the solar cells. So if you observe it and you don't see it, don't worry. It's not because the telescope is not working. It's probably because it's been steered away from this location, and we will basically have additional observation, updates of the TLEs in the future, so you can catch it as well. Let me say hi to people watching us from different parts of the world. Let's see. We have someone from Berlin, from the Nordics. The Nordics can be a lot of places. So
they're from everywhere.
Everywhere. And Scandinavia, the North, the North Pole. Okay. We have Germany. We have someone from New Mexico, from Saint Thérèse, Montréal. Bonjour. Colorado, Maryland, Armenia. Hi. I was there something like a month ago. Beautiful place, beautiful country, amazing. Leicester, UK, Georgia, USA.
That's where I'm from.
Oh, this is your mother. She's watching you.
That's not her, but she probably is.
And the Martha Vineyards in Massachusetts. Okay, good. Let's talk about Uptempo.
Yes, let's talk about some exoplanets. So really quick background. We have a NASA citizen science program that we collaborate with through the Unistellar network. This is called the UNITE program. And we've recently introduced a new part of UNITE called Uptempo, where we're basically looking at potential exoplanet candidates that the test satellite, NASA's test satellite, planet hunting satellite, seems to have missed. So we set our network The observers who observed this did a great job. We had our first Uptempo target. We observed it twice. However, something really interesting ended up happening because it's not a planet. And that's part of science. So there are star systems called eclipsing binaries where two stars are orbiting around each other and they pass in front of each other from our line of sight. And this can essentially create a signature that looks very much like a transit light curve, where the light would be dipping because of a planet passing in front of it. The light from the star would dip. But in this case, it actually appears that a star is passing in front of the star that we were observing. It's an eclipsing binary. It's not a planet. And part of the reason that we know that is because this light curve that we got from the Unistellar network of observers is very V or U-shaped. This is very typical of eclipsing binaries. And the light curve from this result is very similar to the one produced by TESS. So that means that our data are very similar in the light curve that was created from them to NASA's own satellite, which is great news. Except it happens to be an eclipsing binary. We know this because we got some RV data, radial velocity data, from another telescope, which measures the wiggle of a star due to another body that it's gravitationally interacting with. And those data showed that the companion to the star we were investigating was way too big to be a planet, something larger than 200 masses of Jupiter. So we know that it has to be a star. That radial velocity data combined with the V or U-shaped light curve that we're seeing here tells us this has got to be an eclipsing binary instead of a planet, which is still a great scientific result. It's not the planet discovery we were hoping for, but we discovered an eclipsing binary, which is still great.
All right, so you're disappointed, but as you mentioned,
I didn't want to talk about that part.
It's part of science, right?
It is part of science, yes.
Yeah, sometimes you want to make an amazing discovery, and at the end you discover something which is
normal,
okay.
Regular.
It's a meh again, right?
It's a meh.
Yeah, it's all right. So here's a signature of an exoplanet, but it's not an exoplanet because it's way too massive, and we detected that by asking additional observers to take measurements, radial velocity measurements, and they took that from the Observatoire de Haute-Provence. I'm trying to make her speak French, but she refused to do it.
I'm so bad.
Yes, and they took it from the Observatoire de Haute-Provence, the 1.652 meter telescope, which is the place where we discovered the first exoplanet, 51 Peg, in 1995. I was there. I knocked the door and said, "Hey, can you take some data for us?" And they did it. So thank you very much to the director and to the observers for taking this observation. Guillaume, Évrard, and Marc Ferrari, to mention their name.
Thank you.
And that's the way science works. Sometimes you travel and you ask someone to collaborate with you out of the blue, and it does work, and you find out that your major discovery is not going to be a Nature paper.
Yeah, unfortunately not this time.
You're too used to it. You need to sometimes to have some reality check. That's good. All right.
Let's talk about our last thing, Tanager, and then we'll move on to answering some questions.
So Tanager is the new satellite launched by Planet Labs. Planet Labs is a company here in San Francisco. They build small constellation of satellites to observe Earth. And this one is the first one that take what we call spectroscopy observations. So you can detect the surface composition of carbon dioxide and methane. So it's a very interesting and important satellites because it's something that will basically be used to quantify who are the source, who are the emitters of these gases, those gases all around the world. So Tanager was launched again last month, I think. And Planet Lab connected with us, asking us to do some observations of the satellite so we can confirm his location, first of all, see his behavior, and also detect variation of light due to the phase angle that I described before, but also due to the fact that the solar panel was deployed and so on. It's a difficult satellite to observe, and I understand why they ask our network to contribute to this. Because it has a very inclined orbit, so it's observable mostly from the northern part of the world, the Nordics, as we just mentioned. So we have observer in Finland. This is Petri Kuosari, who observed it. Can you see what it looks like? Oh, you saw it.
So the
That's
first one was actually a different satellite. That really bright one was Tanager.
Okay. So we have basically some observation of this satellite. It's quite bright, 2 to 2.5 magnitude. No, 6 to 8 magnitude with variation of light, once again, of 2 magnitude. So once again, it is a huge variation of light due to probably of the phase angle, but also the fact that they deployed the solar panel recently. So we need some additional observation for to characterize the satellite better. We have 7 observations only. So if you live in the north of France and above, check regularly our satellite page and check our prediction to see if you can observe Tanager. It will be extremely interesting to get more observation because right now we rely mostly on our colleagues in Finland. But as you know, the weather may not always be nice in Finland. So if you live above this area, yes, check it out and try to observe it as well. Okay. What
shall we take some questions?
Yeah, let's take some questions.
Yeah.
So, let me say hi to new people who join us. We have someone from Texas. I saw that. Hello.
Hi.
We have England here. We have Northampton, UK, and someone from Normandy and someone from France, somewhere in France. Hello. Okay, so we are going to take some questions from you. Thank you very much for those who took the time to send us their questions. Want to take the first one?
Yes. So the first one is from Scott Cardell. Hi, Scott. When observing an exoplanet transit, I may have picked this question because it's for me.
It's weird.
I know, it's so strange. What's the best way to handle when the target gets too high in the sky? So if you're familiar with the Unistellar telescopes and the maps that we provide to help you plan your observation, on these maps where altitude of the target may be a little bit of a problem, those are denoted by yellow triangles. So just so you know, if you happen to go to our website and see those maps. What happens when a target is really high up in the sky is that the tracking is a little bit harder just because the altitude is so very high. The telescope is basically pointing straight up. The best practice that I have found is to break your observation up into shorter increments. So say that you are observing a transit that's 5 hours in total, which is great. You're doing awesome. You would want to break that up into maybe hour increments so that every hour you can essentially recenter the telescope on the target in case there has been some drift due to the altitude, and then restart your observation for another hour. I know that it's maybe not ideal because sometimes we like to sleep. I don't sleep. I know this man does not sleep, but sometimes we like to sleep.
Humans and they're sleeping.
Yes.
So unnecessary.
But it is best to break up the observation into shorter increments. Maybe not, 1 hour, but at least a couple of different sections if you're doing a longer transit.
Okay. The next question is...
You can take this one. This is from Margaret Luce. When a target calls for multiple acquisitions, are there any disadvantages to performing, say, one continuous observation or breaking it up into smaller consecutive observations?
Well, that's totally related to your answer to the first question.
A little bit.
If the object is located high in the sky, the tracking of the telescope may not be perfect. That's one of the reasons we split in observation sometimes in 3 observations of 10 minutes. So we make sure that you realign basically the telescope. The second part is also if you observe a satellite, or not a satellite, so an asteroid or comet, something passing nearby Earth, flybying our planetary system, our planet, then keep in mind that the position of this object will change quickly. Mm-hmm. So having 3 sequences of 10 minutes where you realign the telescope to the right position, it's better than having one consecutive of 30 minutes, because we may see the satellite, the asteroids, passing by and then disappear for like 20 minutes. So you will have been observing only the sky. and the stars, which are not the goal of the program. So I always recommend to for asteroid to always observe less than 20 minutes, typically, consecutively, and always realign the telescopes. We point the telescope to the right location using the ephemeris.
Thank you. That was great. I'm going to take another exoplanet question really quickly. I'll go through this fast. This was from last time, so I wanted to make sure that we get to it from Felix Mueller. And I will share our beautiful light curve of the Uptempo target that I just had up. So the question is basically, can we talk about what is on our exoplanet reports? Because sometimes these things can be a little confusing if you're not super familiar with them. A few different things you may see on a report like this is the percentage of out of field of view and saturated frames. So out of field of view basically means that there were clouds passing, or the telescope happened to drift away from the target and the target is no longer in the field of view. We can tell because when we run these data through our series of code, it basically looks at the image and plate solves it and tells us where exactly in the sky the telescope was looking. And because of that, we can tell if the telescope was no longer looking at the target or if the target wasn't visible. The saturation can occur with any type of telescope, CCD, CMOS. Essentially, there's too much light coming into the sensor, and that essentially makes the data a little bit unreliable. The sensor no longer responds in a linear fashion when there's too much light hitting the pixels in plain terms. So if the data is saturated, we remove it from the observation, the data in the observation, because we don't want to have data that's not 100% trustworthy, because we know it doesn't respond the same way as a non-saturated image would respond. You'll also see some other things on these light curves, such as the model fit. So basically, we take all of this data and fit a model so that we can tell how long the transit was happening. That's the duration. And we can compare that to what was expected. And also parameters such as the depth, so how much of a dip occurred, and the mid-transit time, which is exactly what it sounds like, the time of mid-transit. And with all of those different parameters, we can compare this to what's known previously about a target, and perhaps there's some transit timing variations where the transit is happening at slightly different times over some period, and that can lead us to other interesting science, or use it to essentially confirm an exoplanet.
Can you tell people why we care about observing exoplanets?
Why do we care about observing exoplanets? Well, they're simply the best.
That's not working. This is not good.
Well, there's a lot that we don't know about our own solar system, and the more that we observe other planetary systems, we find that our solar system is not the common configuration. We want to know more about how our own solar system formed, and in order to do that, the best way is to study our own solar system, but also see what's out there. And by looking at many different configurations of planetary systems, we can get a fuller picture of how planets form, not just in our own solar system, but as a whole. And that leads to our scientific understanding of how gas giants or how rocky planets form, and all of the different variations of systems that exist, including maybe even finding a habitable planet one day. There's a lot of scientific interest in finding planets in the habitable zone, or where liquid water could exist. So there's lots of different reasons for us to study exoplanets.
Okay, thank you. There is some questions. I don't know if you want to take, what telescope do you recommend? Oh,
That's
we are
for
biased.
you, Franck.
I mean, this is SETI Institute has a partnership with Unistellar. So if you want to do citizen science and be part of the citizen science program, that could be definitely the right telescope to use. But I personally, I think you should do your own research and find a telescope which is for you, considering your budget, considering, of course, what you want to observe. Remember, telescopes are generally specialized. Some telescopes are very good for planets, for galaxies. Some are good for observation with naked eyes, with an eye, or with an instrument. The complexity is also a factor. Do you want to spend hours and hours putting together a telescope and a CCD camera and plug a computer and so on, or do you want to buy something fun and cool to use quickly? If you only find something fun and cool to use quickly, the new generation of digital telescopes is truly the way you should go to. Unistellar is one of the brands. I'm biased because I'm a co-founder of the company, so I cannot say much more than that, okay?
You want to take one more question?
Yeah, if telescopes are placed on the moon, how accurate will the data be compared to the ground and hello Earth? Okay, that's a very good question because we are working on something like that. I don't know if I can. Yeah, I think it's official now. There is a project working with University of Louisiana, LSU. It's called Elcam. If you Google Elcam telescope moon, you will find our press release announcement. It's a telescope that will be roughly the size of a unistellar telescope that will be able to observe on the moon. And one of the projects we have is to observe exoplanet transiting exoplanets and comets and asteroids. And the reason we are going to the moon is for multiple reasons. One of them is because a night lasts for 15 days. So it's a long night. You can observe basically objects for a long period of time continuously. Two, there is no atmosphere. Atmosphere are evil for astronomy. They're good for humans, but they're bad for astronomers because they absorb part of the light and they also blur the image. So on the moon, there is no such thing. So we can observe in UV. And this is a very interesting wavelength range. It's beyond the blue. It's not visible to human eyes. Dogs can see in UV. I discovered that recently. But the importance of UV is that if there is water, for instance, on the surface of the exoplanet, we will be able to detect that very quickly with the UV and the scattering light. So that's the reason we want to observe exoplanet on the moon, to be able to detect ocean, maybe, on one of these exoplanets.
It would be so cool. And I just wanted to thank Sabine for the stars on Facebook. Thank you all for tuning in. I think that now we've taken quite a few questions and it's time to wrap up with maybe some upcoming events for the Unistellar network.
Let's talk about Comet A3.
Yeah, Comet A3. Oh my goodness. Do you want to take Comet A3?
Yeah, it's a very bright comet. We have been following it up since last year. I remember when I heard about it, I said, this is going to be the most interesting object in 2024. Nobody believed me.
Here we are.
And here we are. The press is talking about it. So it's a very cool comet because it's passing close to us. It's very active. Ariel has been working. Ariel Gakowski, our lead in comets, has been working on predicting the brightness of this comet, and we have outstanding number, like I think it's going to be -2 visible, and it's already visible in naked eyes. It will reach the perihelion, the closer position to the sun in September 27, so in 2 days. And it will reach perigee, which is the closest to Earth, on October 12th. So now the question is, will it survive perihelion? That's one thing. And how bright will it be? So the recent observations show that it's following basically the brightness, the optimistic brightness that Ariel and other people have been publishing. It's acting truly like a comet, which has a lot of dust. So it's extremely active. So we're doing a contest. Tell us about the contest.
Yes. If you have Unistellar telescope and you are observing Comet A3, please post it to social. We have a contest running from the 27th, from that day of perihelion, because by then it'll be a little easier to observe. It's still going to be an early morning object for that week after perihelion. But our contest will run from September 27th through Halloween, October 31st. And you can go on Facebook or Instagram and share your observations of Comet A3. We will also use those to track its activity, which is why we're asking Unistellar users to submit those images. There's a couple of rules. They're very simple, but each image that you post counts as an entry into the contest. And if you post images from September 27th to October 2nd, right after that perihelion time where we need extra observations, that counts as a double entry. And you could win swag bag, a ticket to the SETI Institute's 40th anniversary event in California if you're a resident here, and also a solar filter is up for grabs as well, a Unistellar solar filter to fit whatever telescope that you have. So it's going to be really fun. I hope to see a lot of people engaging and sharing their images.
I mean, if you can, the dinner is an invitation. If you want to come, you come. If you take even if you're not resident here, I mean, if you are willing to come to the 40th anniversary of the SETI Institute, you are welcome to come, even if you live on the other side of the planet. Nobody forbid you to do that. And we will be there, right?
We will be there. I will be there. I hope you'll be there too.
I will be there. I'm supposed to work with you this day.
Yeah. It's
going
to be fun.
Hopefully it's in my calendar. Okay. The next big thing for the Unistellar users, we have the app 3.5 is going to be released in October. And there is some very cool new features added for the science. And one of them, something we've been expecting for quite a long time, is a satellite mode. So it's a new additional scientific mode that will be added in the app. So it will allow you to observe satellites. We just show you some observation already, but it's going to be much easier, meaning that you don't have to go like change exposure time and all of this. This will be done automatically by the telescope. Once again, Unistellar is really focusing on making this telescope easy and accessible for everybody, so you can do scientific studies easily with just pressing a button on the app. So that's the goal. We will develop this satellite mode in the future with more collaboration with organizations around the world that launch satellites, but also that operate satellites. So stay tuned. It's going to be fun. And then I have a question for you. Not to you, them. Okay. Well, my question is, when you observe, what kind of music do you listen? And can you write it down at the bottom of this? We're going to have a small poll on our community Facebook page. I'm trying to put together a kind of a playlist for observation. So tell us what you listen to, a musician, a style of music, whatever you want. And we will put together a cool playlist for observing the stars. Because don't forget, it's always better to look up than to look down at social media. So enjoy the dark sky.
That would be very fun. Thank you all so much for coming. And I had a great time. We hope to hear what kind of music choices you like so we can observe to them later.
Bye-bye.
Bye.